Section 29.1, Models of the Solar System and Planetary Motion. This is part 2. So we covered the early ideas, and now we're what we consider in terms of human history a more recent, and that would be the two giants in astronomy that revolutionized it. So let's take a look at those two gentlemen and then how that applies to our course. This section is objective. We're going to compare and contrast. In this case, we're going to take the more granular view to what a fellow by the name of Johann Kepler made when he based his second law upon his observations. And then we're going to interpret the solar body's orbital period as a function of its distance in a term we call astronomical units from the sun. So for Kepler, his model and the laws that he developed. He was a German astronomer and mathematician, lived from 1571 to 1630, and he was a very, very good observer and also excellent at measurements. And his boss was Tycho Brahe, who was able to capture and mathematically determine complex motions as seen through these telescopes of the distant bodies. And there's the fellow right there, handsome gentleman. But there's a problem. When he used Brahe's data in his formulations, he not only quantified, but he advanced the work to produce predictions of future celestial events. So not only was he good enough to explain and record, he was able to say what was going to happen next, the predictive power. And from this, he also developed 3 laws of motion that successfully explain almost all aspects of planetary motions. First was the law of ellipses. And the first law states that each planet orbits the sun in an elliptical path, not a circle. Up to this point, everybody thought it was a circle. An ellipse is an oval, instead of a circle, has one focal point in the center. It has 2 focal points, one at each end, as opposed to the single point of the center. Each focal point is called a focus. So we have one up here that shows you. This is the ellipse, and these are the 2 focus. Total focal points. And for an ellipse, if you pick a point anywhere on its pathway, doesn't matter where you pick it in its orbit, and you connect with that point with a straight line for the 2 focus, the sum of those 2 lines will always be the same. So in this case, you pick the spot right here. If you take that to one focus, measure that line, and measure this line, and add those up. No matter where I go, if I go this way, this line gets shorter, this gets longer, the 2 will still always have the same length. And because they're ellipses, the planets are not always the same distance from the sun. There's a point where they're actually the closest to the sun, called the perihelion. There's also a point where they're farthest from the sun, aphelion. So Earth itself is a point where it's actually closer to the sun, as at its perihelion, where it gets the farthest point, the aphelion, is actually farther from the sun. The orbital distance for a planet is the average of the perihelion and the aphelion distance. So you realize if you know the short distance and the longest distance, add them together and divide by 2, that is our orbital distance. And for us, the aphelion is about 152 million miles from the sun here. And at the shortest, it's about 147, the perihelion. So if we add those two, 152, 147 together, and divide by 2, our average orbital distance is 149.5 million miles. We use the Earth, since that's where we live, and we're the observers. Our average distance from the sun is called 1 AU, or 1 astronomical unit. So it's the average distance of the Earth is 1 AU. So when we're talking about stuff inside our solar system, we use this measurement. Although the planets are either fractions of 1 AU, means they're closer than us, or multiples, which means they're farther from the sun than us. And the law of equal areas is his second law. In this one, he said the speed at which the planet travels at different points in the orbit changes. So there's longer sweep arcs and then there's shorter sweep arcs. So Tycho Brahe's data told Kepler the Earth's velocity is faster when it's closer to the sun. If you kind of think of something when you're bringing it in, like a skater again, and then slower as you get farther at the aphelion. So for any given duration of time, if you connect the sun to the sun, where the Earth is drawn, and it revolves, it'll sweep an arc area from the start to the end time. And Kepler said the sweep area close to the sun would be wider, but faster. And the farther out would be narrower, but quicker, slower, excuse me. So he said, right here close, it sweeps around here faster, so it's making a bigger area. Whereas out here, it's moving slowly. The triangle's narrower, and the area is smaller. So the orbital period is the time required for the planet to make one complete revolution about the sun. So imagine, the sun's moving around the Earth's moving around the sun. We knew what a year is, but we really couldn't quantify that until this point. So the law of orbital periods describes the average distance from the sun and the orbital period for the planet itself. How long does it take to go around the sun? According to this law, it's the cube of the average distance is proportional to the square of its period. That's a mouthful. But what it really comes down to is this. That speed, k times r cubed equals p squared. K is just a plug number to make this thing balance. He liked r cubed equals p squared, but it wasn't quite right. So you need a little plug number to make it balance out, make them equal. It's equal to 1. So r is the distance to the sun in astronomical units. P is the planet's orbital time in Earth years. This way he can now calculate how long it took other planets to get around compared to ours. So the Earth is 1 astronomical unit from the sun, and it orbits 1 Earth year. Thus, he used the k times r cubed equals p squared. Well, k is 1. Our orbital distance is 1 astronomical unit, the radius. And the time period is 1 year. So obviously ours is going to balance out. And this is his base equation. So 1 equals 1. That basically comes down to his laws. So we take a look now at Jupiter. This is what made them all excited. Jupiter, you calculated, was 5.2 astronomical units from the sun. So it's 5.2 times farther out than Earth is. And it takes it 11.9 years to orbit the sun once. So does this hold an agreement? Well, we have k equals r cubed equals p squared. So k is 1. What's the orbital radius? 5.2, because remember it's the distance from the sun to the farthest point, or the average. I'm going to cube that number. So I'm going to take 5.2 times itself 3 times. Does that equal the distance, 11.9 Earth years squared? We take 1 times anything is 1. 5.2 times 5.2 times 5.2 gives you 140.68. 11.9 times 11.9 gives you 141. So they're approximately equal. So effectively, it's an agreement for this planet. This is how we can back calculate how long it takes a planet to go around the sun or its distance. Newton came along later. He says, hey, I like those laws. I'm going to apply those. So he explained how planets move about the sun. He also explained why they move the way they do. So we not only capture the why of the object in space, but also for Earth. His hypothesis, an object in motion stays in motion unless something outside of it, force, works and acts upon it to slow it down or speed it up. And objects will move in a straight line at a constant speed, and it will keep doing so. This is called inertia. Examples of inertia: if you put a cup with a piece of cardboard and a coin on top, and you pull this out real fast, this wants to stay at rest, but once you pull it out, it'll just drop straight down. There's other examples of inertia. It also applies to the object at rest. It'll stay at rest, again, unless something outside force acts on it and makes it move. This is at rest. When you pull it away, the outside force's gravity will make it move. He also said moving planets don't fly off in a straight line somewhere else is because there's an outside force acting on them. He called this outside force gravity. First time anybody came up with this, that there's a force that's keeping it in its inertia or its motion, or a gravitational force. He also said that they're in orbits around the sun, so there must be a gravitational force keeping them there. And there's no other outside force drawing them off in a different orbital plane. It's got to be the sun. And that's the end of this section.